Thank you, Ida. So after 3 days of chemistry, you think that you are out of trouble. In fact, that's just the beginning of your troubles. And now it was relatively simple, in fact, with this chemistry. We heard about all the details and, the guidelines. And now we are going into experimental design. And we started already yesterday with Chris's presentation. Now there will be a little bit of overlap between his presentation yesterday and mine, but I think it will be minimal, hopefully. So I will look at approaches and tools to manipulate the carbonate chemistry. And I'm using 2 main sources of information which are included into the syllabus. The first one is a technical note that Héloïse Lavigne and I published recently in Biogeosciences. And the second one is a chapter in the guide for best practices on ocean acidification research and data reporting that hopefully will be published early next year. But this draft is already available on the, it's not a draft, it's a revised semi-final version. It's already available on the EPOCA website. So what we are doing when we are doing perturbation experiments, we are trying to in fact, investigate the response of an organism or a community to changes in the carbonate chemistry. So we do a control at present day, most often, carbonate chemistry, and another kind of measurements at different levels of PCO2, for example. I think the first purposeful perturbation experiment for ocean acidification research was performed by Catherine Aghegian. She was a student of Fred Mackenzie. And she did some work on coralline algae. And with, this ocean acidification has become a hot topic, and now lots of newcomers come to the field, mostly biologists. And I think it's very important that training courses such as this one are organized, and also that guidelines are provided to the newcomers to make sure that the experiments carried out will be really useful and significant. As we have seen earlier this week, the whole guidelines for the carbonate chemistry are already available. That's the Dixon et al. Guide. And the purpose of the EPOCA guide is to provide, guidelines for really designing perturbation experiments. So when we do perturbation experiments, the carbonate chemistry can be manipulated in various ways. Some are more useful than others, and some are problems. Others are more or less recommended. So I will try to go through all those methods. And therefore, the goal of this presentation is to look at the benefits and drawbacks of the various methods used to date, to provide 5 new C-carb functions which can be useful to assist the design of perturbation experiments. Also to provide some guidelines on to choose the PCO2 levels to be used. And this is from a chapter of the guide, the EPOCA guide by Jim Barry. And finally, to provide other recommendations on the experimental setup. So I will skip the introduction to C-carb. Usually I do that, but I've done it on Monday morning. And then I will focus on the main approaches. The first way to manipulate the carbonate chemistry is to change DIC at constant total alkalinity. And it can be done 3 ways: by gas bubbling, the addition of strong acid, as well as carbonate and or bicarbonate, and also mixing high CO2 water with regular seawater. Also, one can use changing total alkalinity at constant DIC, that's the addition of acid. One can change both total alkalinity and DIC by adding bicarbonate and carbonate, or we can also manipulate the calcium concentration. Although that is not technically a change in the carbonate chemistry, it can be useful when working with calcifying organisms to investigate the impact of the saturation state on calcification. Then I will go to the guidelines for choosing PCO2 levels. I will look at how we can maintain the chemistry during the experiments, provide other recommendations, and then summarize and conclude. In all the examples that I will provide, I'm assuming that the atmospheric PCO2 is 384, the target PCO2 793, the salinity 39.9, temperature 18.9. I'm doing the calculations for surface water, so hydrostatic pressure of 0. And I am assuming that the total phosphate and silicate concentrations are also 0. And very important, I mean, those techniques which I will describe are described to set the initial carbonate chemistry. And it's a different story, to maintain this carbonate chemistry constant, and I will address this later. So what are we trying to accomplish when we do a perturbation experiment? We want to have a control, most often at present-day values, which are here, PCO2 384, that's my assumption. This pH, total alkalinity 2325. The carbonate ion concentration 187, and those are the saturation states of calcite and aragonite. And we want, for example, to use a second PCO2 level at attempting to mimic the carbonate chemistry in the year 2100. For example, PCO2 of 793, pH 7.793, and what else? The carbonate ion concentration 1110. You see that the total alkalinity is not changed. And this has been mentioned several times during this meeting, but in fact it will change, most likely. There is some modeling work done by Rick Zibi, Christoph Heinze, and I forgot the name of the first author. It's a Russian. No, it's a Russian postdoc working with Zibi. I forgot her name.
Oh, Tatiana.
Tatiana, yeah, okay. So they do show that, in fact, in the year 2100, due to the decline of calcification, total alkalinity will rise by perhaps 15 to 30 micromoles. But for the sake of this experiment here, I'm going to assume that total alkalinity doesn't change. All right. So the first group of methods is to change DIC at constant alkalinity. Sometimes I'm using TA, sometimes AT. I'm getting confused now because of Andrew. So I should use AT. Gas bubbling, the first one. Obviously, it's a system open to the atmosphere, otherwise you're in trouble. TA is not affected. And if all goes well, after a while, PCO2 will reach the value of the bubbled air. That's for the initial state. That is when you don't have biological processes, messing up your chemistry. And for example, one can use, the present-day PCO2 384, and we are going to use seawater at 2325 micromoles per kilogram total alkalinity, and we are going to bubble with 793 microatmosphere PCO2. So there is a CCARB function. Now you may be more familiar with how it works. So the function is P gas, perturbation through a gas bubbling. The flag here indicates that we are using two variables, and those two variables are PCO2, the initial PCO2, and total alkalinity. That's the partial pressure of the gas used to bubble, salinity and temperature. So the function returns two lines. The first one is the initial conditions. So if we look at PCO2, 384, and the second line are the final conditions, 793. And you have all the other parameters provided here. So we have reached the target PCO2 value after full equilibration. So using this function, you can build this kind of figures. I'm not going to spend too much time on them, but it shows the PCO2 of the bubbling gas and the resulting seawater chemistry here, PCO2, pH, total alkalinity, DIC, and here are saturation states of calcite and aragonite, and it shows the decline, for example, of pH before and after the perturbation. B is before, A is after. So the pH has declined to the target value, PCO2 has increased to the target value, etc. So therefore, if we look at the full results of gas bubbling after full equilibration has been reached, we are on target everywhere. PCO2 is on target, pH, total alkalinity, obviously, because we didn't change it, and the carbonate ion concentration and the saturation states of calcite and aragonite. So this method is really recommended. It's an efficient way to reach target values. I think the first example of use of this technique is a paper by Steve Smith and Roth. I think they investigated algae. I think it was coralline algae. And there are two ways, once the target PCO2 is reached, two ways to maintain it. The first way is to use a pH stat or PCO2 stat. That is, pH is monitored and total alkalinity is assumed constant. If it is not constant, it must be measured frequently. And a controller opens and closes valves when pH is away from the target value. Valves that inject either acid or base, or air and pure CO2, or CO2-free air and pure CO2, or CO2-free air, air and CO2. Various mixtures have been used until now. CO2-free air can be obtained several ways, using CO2 scrubbers, but also using molecular sieves. There are companies producing CO2-free air using generators. We have one in the lab, and it works quite well. The drawback of the pH stat is that regular calibrations are needed. And when we do this kind of experiment, usually we calibrate the pH electrodes every day. For long-term experiment, that's very time-consuming. The other way to do it is to bubble with premixed gas, either purchased from a company or made with mass flow controllers or gas mixing pumps. There are several companies producing gas mixing pumps, but their flow rate is very low. So it's okay for small volumes, but not for very large volumes. So this enables to have a good control of pH and PCO2. It compensates all the changes if you have the right bubbling, the right volume, etc., the changes due to photosynthesis and respiration, but it doesn't compensate for the decline of total alkalinity or calcium with calcifying organisms. So that's something to keep in mind. If you have calcifying organisms, you want to watch total alkalinity and the calcium concentration, and you may need to supplement total alkalinity or calcium. And this method is not suitable for some microalgae, which don't like to be bubbled. So that's an issue also. Perhaps you want to bubble in a different header tank, for example, and then put the outflow in the experimental vessel. So that's something to take into account. Also, bubbling is sometimes problematic when you work with microbial processes, because it promotes coagulation of dissolved organic matter into particulate organic matter, and it may trigger changes in the bacterial community that you may not want to see, which will confound the experiment. So it can be relatively precise. That's an experiment we've done with Antoine Siandra in the years 2000, and we can get very good control of PCO2. That's in a chemostat, and these are days, 3 weeks approximately of experiment. So it's used very frequently, as I said. This is work being done at the Marine Lab of the International Atomic Energy Agency. They do work on fishes, theropods. That's an example of a PCO2 stat used by Frédéric Gazot to investigate the response of mollusks, bivalves, to ocean acidification. So here he's monitoring PCO2 using an equilibrator and an infrared gas analyzer. and the valves are controlled by the CO2 level measured in those experimental vessels here and there. It has been used in chemostats. These are the chemostats we used with Antoine. And also, that's an example of the use of a header tank. That's the experiment in Spitsbergen in May this year. So PCO2 was controlled in a large volume here using a pH stat. And then there was an overflow in experimental tanks which were downstream of the header tanks. So that's it was an open flow-through system, of course. And also, it was used in Bergen for the first Bergen mesocosm experiment. Bubbling was done initially to reach the target PCO2. The second method is to mix regular seawater with high CO2 water. For example, in the example I'm showing here, you can mix this weight of seawater at a PCO2 of 384 and this total alkalinity with a smaller weight of seawater saturated with CO2. In this example, 10 to the 6 microatmosphere, and the same total alkalinity. There is a C-carb function for that, Pmix, which is shown here. So the variables are, the first ones are always the same. This one is PCO2 of the high CO2 seawater. The weight fraction of the two weights, salinity and temperature. So let's have a look, PCO2. So we had 384 at the beginning, and we end up at 792, which is the target PCO2 value. So that's something that works for PCO2. This I will skip. And if we look at the other parameters besides PCO2, all the other parameters of the carbonate system are on target. pH, DIC, the carbonate ion concentration, and the saturation states of calcite and aragonite. So that's also a method which can be recommended. I think it has not been used very often. To my knowledge, only twice. Once by McGrosh, is in this room there, and once by Kai Schultz and colleagues using the Kiel mesocosms. And so, for example, Kai used 100 liters of water supersaturated with CO2, and he mixed it in 60 cubic meters of seawater. Those mesocosms are 60 cubic meters. I am told by Kai that it is not easy to precisely adjust to the target PCO2 because you have 100 liters of supersaturated water. It's covered, you uncover it, you pour it using a pump, I think. You mix it into your large 60 cubic meters mesocosm. And it's not really easy to adjust, he says, to the target value. But in the lab, it should be much easier to use. A third way to manipulate the carbonate system at constant total alkalinity and changing DIC is a two-step procedure. The first step is to add, which was mentioned already yesterday by Chris, to add either bicarbonate or carbonate in order to elevate DIC to the target value, and then to add acid at constant DIC to cancel out the increase of total alkalinity generated by this addition of carbonate and or bicarbonate. So in this example, we mix, we add carbonate, 15.3, 10 to the minus 6 moles per kilogram, and bicarbonate there's something missing here, to seawater, and then we add acid. The acid part is missing from this sentence. In fact, we add acid. We add 14.18 milliliters of acid, 0.01 normal. Sorry, there is something missing here. So that's acid addition is designed to restore total alkalinity to the initial value of 23, 25 micromoles per kilogram. So if we look at, again, there is no specific C-carb function for that, but you can combine two. I can provide details if you like. But if we look at the result, the initial PCO2, that's the wrong slide. Here it should be 384. I have mixed up the slides yesterday. And 384, and we are on target value, 793. So this is also, trust me, a method. Even though the slide is confusing, it's a good method to reach the target values. And if we look at the end results, in a closed system, we have after acid addition here, we are on target everywhere. PCO2 793, pH is on target, all the others, the carbonate ion concentrations 110, and the saturation states of calcite and aragonite are also exactly on target.
Are you doing that with sodium carbonate or
sodium carbonate, yeah, or bicarbonate, yeah. I will come back to that in a while. Then this is a method that can be recommended. It has not been frequently used. Perhaps the first time I have seen this in the literature is a paper by Borowicka. He also worked on calcification in algae, macroalgae. It allows a very precise control of the carbonate chemistry, but I don't think it can be used in flow-through systems because adding this carbonate or bicarbonate will be tremendously complicated. I think you could use a peristaltic pump, etc., but that will be really too complicated. So now we are going to another way to manipulate the carbonate system is to do it at constant DIC, but changing total alkalinity. So we can have a system closed to the atmosphere. That's the one that is most often used because the second one is really useless. So the DIC is not changed because the system is closed to the atmosphere, and we decrease total alkalinity by adding acid, or we can increase it by adding a base. When it's open to the atmosphere, it's useless because obviously there is gas exchange, and through equilibration, PCO2 comes back to the atmospheric value, so that's not really useful. So the example is to add acid 0.01 normal HCl to 1 kilogram of seawater. In a closed system, there is a C-carb function for that, PPH, perturbation of pH. Cis shows that the system is closed to the atmosphere, Cis equals 0. And then we add here the volume of acid. By convention, when we add acid, it should be a minus here, 14 milliliters of acid. And this is the normality of the acid. And if we look at the PCO2, initially 384, and then we reach 792, 793 after acid addition. That is the target PCO2 value. And if we look at the other parameters in a closed system, the first line, so the PCO2 is on target, but the pH is not, and none of the others is. The proton concentration obviously is not on target. The total alkalinity is obviously not because we have decreased it by adding acid. So we have 2184 instead of 2325. The DIC is not also on target, obviously, because we worked at constant DIC. The carbonate concentration is lower than expected, as well as the saturation states of calcite and aragonite. So you see that even though we have reached the target value for PCO2, all the other parameters are off target. So I don't think we can recommend this technique, although it has been very, very often used. And the first paper I have found is a paper by Buxin in 1926. He looked at the calcification of sea urchins under acidic conditions, and he measured pH with paper pH. That's a very interesting paper. It's very short. In fact, it's a series of 2 papers, 2 pages each. Very nice. That can be used in a pH stat, and also it has been used in flow-through systems. And that's the cover page of Aghegian's thesis. She used this method of acid additions. So we can also change total alkalinity and DIC by adding carbonate and or bicarbonate. There is a function for that, PTA. Now you get familiar, perhaps. The system is close to the atmosphere, Cis equals 0. So we add carbonate here. That's the, we don't add carbonate. Here it's 0. We add bicarbonate, this amount in moles per kilogram. And when we do that, we see that indeed we reach the target value for PCO2, 793. But all the other parameters are off target. And obviously, most importantly, total alkalinity and DIC are way off in a big way. pH has decreased, but not as much as it should have. I mean, if we wanted really to mimic the year 2100, you see here we have 7.9 instead of 7.8. So this method is really not recommended. It has been used, or however, often to manipulate the carbonate chemistry, mostly to investigate the physiological response and to investigate whether calcification or photosynthesis are limited by the amount of DIC. So it's more like a physiological kind of technique rather than a technique to be used for the purpose of understanding the impact of ocean acidification. It can also be used for ocean acidification studies, but that is to restore the saturation state. I think Chris has used it in the Biosphere 2 in order to restore total alkalinity because he was doing long-term experiments, and due to the calcification, total alkalinity was getting down. So he didn't use it to manipulate the carbonate chemistry, but to restore normal alkalinity in his experiments. And the last method is to manipulate the calcium. Again, it's not a useful way to investigate ocean acidification, but it has been used in this context because some calcifying organisms respond to omega, the saturation state of calcite or aragonite. And it's a useful way to understand the calcification process. So usually it involves the use of artificial seawater with a non-total alkalinity and DIC, and to set the calcium concentration to the value you want. Instead of about 10 millimoles per kilogram, in this example, I set it to 6 millimoles, for example, to decrease the saturation state. And obviously, if we look at the end result, none of the carbonate system parameters have changed here. So we are off target for all of them for the purpose of ocean acidification. Only omega calcite and omega aragonite are on target because we did manipulate the calcium concentration. So obviously, it's not recommended to use calcium manipulations for ocean perturbation experiments. You can find it useful for physiological purposes. I have used it in corals to investigate whether calcification in corals was generating CO2 to be used by photosynthesis. So if you incubate corals at a low calcium concentration, you switch calcification down, Therefore, you switch the generation of CO2 down, and you can investigate photosynthesis, whether it is decreased by the lower rate of calcification. So that's mostly a physiological way to look at it. However, it has been used, calcium additions, to replenish calcium during long-term experiments with calcifiers. Chris has done it again at the Biosphere too. So in summary, we wanted to jump from the carbonate chemistry in the year 2007 to the year 2100. And we have three methods which enable to go right on target. These are gas bubbling, the addition of high CO2 seawater, and the addition of carbonate and or bicarbonate and acid to seawater. All the others are in a way or in another not suitable because some of the parameters are not on target. That being said, yesterday Chris compared the comparative effects of acid addition and gas bubbling. Acid addition in these graphs, the lines are in blue and gas bubbling in red. And we look at DIC, total alkalinity, and all the parameters of the carbonate system. So what Kai is doing in this figure is showing us that despite the fact that the addition of acid doesn't mimic the increase in DIC that is obtained with gas bubbling, DIC is constant by definition. All the parameters, except, of course, total alkalinity, go in the same direction. The CO2 concentration goes up, of course. The pH goes down. And the two methods, you see, go in the same direction. Sometimes there is a large gap between the two, for example, here for the bicarbonate concentration. But the bicarbonate concentration increases in both cases, as well as omega calcite and aragonite. So to conclude, I've tried to put this table together. The target values are reached for those three techniques. This is my perceived ease of use. Obviously, it's quite easy to add acid and to restore TA, and it's not costly. Gas bubbling, so it's not really easy to add acid and restore TA because it's, as I said, it's sometimes difficult in large volumes to reach it, to reach the exact and precise target value. Gas bubbling is dead easy. We just need to buy sometimes gases, but if you want to make them, the cost can be relatively high. Mass flow controllers, gas mixing pumps do not come very cheap. Mixing with high CO2 seawater, it's not so easy to reach the target values, but and the cost is very nice because it's not expensive at all. That's not typically a perturbation experiment, but it's a natural perturbation experiment. That's the one I mentioned yesterday, the island of Ischia, which can be useful for to investigate, the response of benthic organisms to changes in the carbonate chemistry. These are those vents, and you see very close to the vents there is obviously nothing. I guess perhaps Caroline, you know better than I do, but 7.2 the pH around the vents, or 7.4, very low pH. And then a little bit distance, there is a lush seagrass bed, Posidonia oceanica. And you see even inside, the vents are also around the Posidonia. That's Jason looking at the release rate of CO2. That's almost pure CO2, 99.9% CO2. There is no sulfur. And these are calcifying organisms. The calcium carbonate is gone at the tip of those gastropods at, I think, a pH around 7.6. Now, the guidelines for PCO2 levels, there is a chapter in the guide for best practices by Jim Barry and colleagues, and they put together this table. We had a very long discussion in Kiel about that because recommending CO2 levels, everyone has his own idea. But anyway, we came up with this kind of table. If you are limited to 2 treatments for cost reasons or because you don't have the equipment required to do more, the recommendation is to do present day and 750. If you have 3 treatments, it's perhaps a good idea to look at pre-anthropogenic values of PCO2, 4, 6, 8, etc. These are just guidelines, obviously. You may want to use much higher PCO2s, like our physiological colleagues, Ansoto, Portner, and I presume Bright Seibel are also using very large PCO2 values in order to understand the physiological and molecular mechanisms involved in ocean acidification. And also, you may want to also target PCO2 values for calcifying systems in order to be close or just a little bit below the saturation state. So this is meant to be seen as guidelines, but it's obviously not carved in stone. So that was to set the initial carbonate chemistry, and and obviously there are more complications afterwards because you want to maintain this carbonate chemistry or during your experiment, or you want to avoid large shifts of the chemistry. And the first process, of course, that complicates your experiment is the CO2 invasion and release. I have taken this figure from a book which has not been mentioned so far, and I really recommend this book by Zibi and Wolf Gladrow. I think there is a newer edition. This one is 2001. And this is really a very nice book on the seawater CO2 chemistry. Very, very well done. So this graph shows DIC and here on the x-axis, total alkalinity on the y-axis. And it also shows pH, the dotted line here, 8.2, 8, 7.8, and the CO2 concentration here, 30 micromoles per kilogram, 20, etc., down to 8. So obviously, CO2 release in your case, because you are going to work with high PCO2 water, will decrease DIC. So you will go away from the target values at obviously a constant alkalinity. So in effect, you will decrease the CO2 concentration, from about 13 to about 11, and you will also increase the pH from about 8 to somewhere about 8.1. So that's the first complication when you have set your initial chemistry. And if you have organisms in your tank, obviously one way for the organisms to manipulate is to do photosynthesis and respiration. Here is one way to look at photosynthesis in this direction, producing organic matter and oxygen. And you see that there are 18 protons consumed per 106 moles of CO2. So there is a change in alkalinity with photosynthesis and respiration, which in fact depends on the nutrient used. In this case, it's nitrate. It's different for ammonium. So total alkalinity changes a little bit. When you do photosynthesis, total alkalinity tends to increase a little bit, and obviously it decreases by 17 moles per mole of CO2 uptake. And also DIC changes with photosynthesis. DIC decreases and increases with respiration. The other process that messes up your chemistry is calcification or precipitation and dissolution of calcium carbonate. Precipitation goes into this direction. You generate calcium carbonate. Dissolution goes in the other direction. And there is a stoichiometric relationship between the change in DIC and total alkalinity. total alkalinity decreases by 2 moles here, 2 bicarbonate, for each mole of DIC consumed. We are consuming here 2 moles of DIC, but generating 1 here. So calcium carbonate dissolution and precipitation change not only the DIC, but also the total alkalinity in a 2-to-1 ratio. So that's why those are processes, obviously, that must be taken into account to maintain the chemistry more or less constant or with little changes in your experiment. In closed systems, the incubation should be short enough to avoid a large drift of the chemistry. And in open systems, you want to have a control mechanism which is efficient. Chris mentioned this yesterday, and you want to have the right biomass to volume ratio, whether you use bubbling, a pH stat, or a PCO2 stat. Again, it's important to remember that total alkalinity and the calcium concentration cannot be controlled by bubbling, obviously. So that's another reason to have either a flow-through system or an incubation in closed system that is short enough. So the critical issues to consider are the biomass to volume ratios. You don't want to pack the aquarium with too many of your organisms. You want to keep the duration as short as possible in closed systems. And in open systems, you need to set the residence time of the water. In flow-through systems, I mean, you want to set the flow rate in order to have the right residence time so that you don't, the biology doesn't affect too much your chemistry. Other recommendations, filtration. When you sample, for example, a phytoplankton culture, when you take seawater to make a culture medium, you need to often to filtrate it. So filtration obviously alters the carbonate system. So it is important to do the filtration before you manipulate the chemistry. And if it cannot be done, the carbonate system must be reassessed after filtration. Otherwise, you may end up with values very different from what you expect. This has already been mentioned. Gentle pressure filtration through a cartridge should be used rather than, vacuum filtration in order to avoid the damage of cells, which can increase the alkalinity. Autoclaving is used by many of us, especially when doing culture medium. Autoclaving changes considerably the carbonate system. Almost all the DIC is lost during autoclaving. And therefore, the perturbation of the chemistry should be done after you have autoclaved your seawater.
But that's for an open system, when you autoclave it open. If
Yes.
you autoclave it closed, it stays there. It takes days before everything redissolves, but it stays there.
Yes, yeah. So now you have set your targets values. You want to maintain them. For gas bubbling, it's important, obviously, to make sure that the equilibrium has been reached before you start the experiment. And this is not trivial. It can take several days before you reach your target. For the mesocosms in Bergen, I believe they were around 10 cubic meters. It took 3 days to reach the target PCO2. And during the experiment, the required time depends obviously on the biomass to volume ratio, the PCO2, the gas flow rate, the size of the bubbles, the volume and shape of your experimental vessel. Something quite important also to consider is the fact that CO2-free air generated by some of the generators I mentioned before, and also the premixed gases are waterless. So it's critical to minimize, if you work in small volumes, like in beakers or small flasks, to humidify the air before bubbling, in order to avoid changes in salinity. Obviously, once the target value is reached, you don't want to have air-seawater exchange, so no autoclaving, vacuum filtration, or temperature changes. Unless you bubble and you constantly monitor and set your chemistry, it is important to use gas-tight bottles. That's without headspace. That's what we use for phytoplankton work. So I already told you that the biology can severely shift the carbonate system. So the biomass to volume ratio is very important. Not only in closed systems, but as Chris showed yesterday, even in a flow-through system with continuous bubbling, you still have, those changes. It can be you may want to keep those changes, but you really want to make sure that they're not too large for your experiment. And again, extra care with calcifying organisms due to the changes in DIC and calcium ion concentration. Another aspect is the contribution of dissolved organic matter, inorganic nutrients, and pH buffers to total alkalinity. Phytoplankton releases DOM, which can contribute to total alkalinity. And there is a recent paper by Lee and colleague showing that this, in a phytoplankton culture, this can be really significant. It depends, the contribution seems to depend on the species considered and the age of the culture. But if you have a relatively high biomass to volume ratio, you may want to avoid using total alkalinity to constrain your chemistry. You may want instead to use DIC and PCO2 or pH and DIC. Also, physiologists sometimes use pH buffers in order to keep the pH constant in their experiment. That has been done already. If you want to do that, I mean, those buffers increase total alkalinity. And again, the same thing. You may want to avoid total alkalinity to characterize the chemistry and focus on a different pair of parameters. Inorganic nutrients, mentioned a few days ago also, can contribute to the alkalinity, especially phosphorus and silicate. So if you work with culture medium, it's critical to measure phosphorus and silicate and to use them in CO2-Cs or C-carb in order to derive the chemistry. Also, photosynthesis and respiration change the nutrient concentration, and those changes also affect the total alkalinity. I'm providing here two references, and therefore, in those instances, it's important to measure ammonium, silicate, and phosphate. Finally, when using isotopic labeling, adding C13 or C12 or C13, sorry, or C14 in your experiment is in itself a manipulation of the carbonate system. So you need to take this into account. It requires obviously the same precautions than the precautions used to manipulate the carbonate chemistry that I mentioned before. Also, you may, depending on the activity, you may add sodium salts, which can change the carbonate system. Obviously, no bubbling and no headspace load. So those, again, those guidelines are available on this, in the guides. At this time, only revised semi-final versions are available. But if you go to epoca-project.eu and you go to here on the menu, there is a menu item guide to OA research. And then you will have, if you scroll down, you will have access to the most chapters, including Andrew's chapter there. So I'd like to thank Héloïse Lavigne, who helped me with revising C-Carb recently. Also my co-authors for the chapter in the guide, Kushnan Gao, Kita Kli, Bjorn Rost, and Kai Schulz, and obviously financial support from the European Commission through EPOCA. Thank you. Yes?
Yeah, I have two comments. One is just very brief, but if you wind up using radiocarbon methods, let me ask you to always be sure to inform your colleagues and collaborators that you're doing so, because there are many people who, in other parts of their life, work with natural abundance levels of C14 in particular, and so, which is a huge issue. So, you know, it's not that you couldn't do it, but that you need to be sure that you let people know that that's something you've done in the last 10 or 15,000 years, so that they think about it.
Sure.
And the other comment has to do with the first part of your talk. And I certainly completely agree with the sets of manipulations that you suggested for matching ocean acidification in terms of the whole suite of carbonate parameters. But I would note that using some of the other methods can provide a way to investigate the influence, sort of the mechanism, if you
Yes.
like. And so, for instance, there are ways to look at changes in saturation state that either are positively or negatively correlated with bicarbonate, for instance. And so, while I completely agree with the manipulations you suggested, if the goal is to, as closely as possible, mimic what we think is going to happen in the next 100 years, there may be a lot to be learned by using some of those other methods as well as a way to pull apart different mechanisms or influences.
Of course, I fully agree. And I said, as I said, you know, it's a nice way to understand the processes. Yeah.
Maybe I could just embellish on that idea, which is that all the methods you showed involved adjusting alkalinity and DIC. Sometimes you only adjusted one.
Yeah.
Sometimes you adjusted both of them. And if people think about that, what you'll realize is you can only adjust two things, and then everything is fixed. So that's the properties that I was talking about of the CO2 system. So you can't get everywhere on the possibilities. You can't independently change CO2 levels, bicarbonate levels, and carbonate levels. But you can control two of those at any time. So if your experiment wants you to know the bicarbonate and know the carbonate, you can change the alkalinity and total carbon to achieve that. If it wants you to know the CO2 and the carbonate, you can do that. You just can't do all three, ever. The other question I had is in regard to the bubbling. Our experience is that when you're trying to get low CO2 levels, bubbling takes forever, or close enough to forever that it doesn't matter. How do you deal with that, getting like 280 or 180 as the levels you're talking about?
I have not done myself those experiments, so I don't have any idea for that. What I have done is, clearly when we did these chemostat experiments, it's obviously very easy to overshoot for CO2. And when you do that, when your control system, you know, provides one too many bubble, then boom, PCO2 goes way up 1,000. And then to go down to 700, you know, it takes 2-3 hours by bubbling with CO2-free air. I mean, I don't know how to get around this. I mean, that's a very slow process to get down. And obviously, you cannot increase. We were working with phytoplankton cultures, so there was no way we could increase, you know, the bubbling rate tremendously. We were set, yeah.
I haven't done that myself either, but I have seen, I have seen a couple of papers where they gas strip first. Acid strip first. They acidify the seawater to strip out the CO2, and then add that CO2 back in a very closed, controlled system, and then readjust to allow when they need it. I'm not convinced it works very well, but I have seen that in a few papers.
Okay. Yeah.
So the way that I've done that with a sort of pH setup is that I bubble constantly. These are small 4-liter open systems, non-closed. And I bubble constantly with stripped air so that keeps the water oxygenated. But then I intermittently add back CO2, and I'm able to reach this pre-industrial concentration fairly quickly, so it doesn't take terribly long. But what I found was that if I bubble constantly with stripped air and then add CO2 back, I can maintain this at lower ambient conditions.
Yeah, that's what we do now too. I mean, in our area, I mean, the air from the outside, the PCO2 swings too much. I mean, for us, so all the changes, reflect, of course, in your tanks. And in the bay, for example, when cargo ship or passenger ships come in, I mean, there are fumes, and then the PCO2 goes to 500, 550. So in order to avoid, having those large changes in CO2, we just strip, as you say, the CO2 from the air, and we add up CO2 to it. So that's really the best way to go. Otherwise, any change in the atmospheric PCO2 will reflect in the tank, and that's not something you want to do.
I have two questions for you, JP. My first question is, you presented some suggested target levels of the
Yes.
CO2. And as we know, some ecosystems, for example, coral reefs, are already typically way supersaturated with respect to atmospheric PCO2. Wouldn't it be more useful maybe to suggest delta values rather than fixed levels? Because maybe several of those levels are already lower than we would see in the future. And my second question is, in EPOCA and the best practices guide, have you thought of and discussed the best practices for carbonate dissolution experiments? Because that's the other side of the story. We may be mostly concerned about the effect to biological organisms, but there's going to be carbonate dissolution as well.
Okay, the first, I already forgot the first question. What was it?
Delta PCO2.
Delta PCO2. I don't understand why you mean that some coral reefs are already above those values. What do you mean?
Well, I mean, the PCO2 in the seawater, for example, in Coral Reef Bermuda, is well above the current 390 microatmosphere, maybe 450, sometimes close to 500, and sometimes even higher than that.
In Kaneohe Bay, the average is probably 500 ppm today.
Yeah.
Because the calcification is raising the PCO2.
That's not the case in most coral reefs I am aware of. I mean, you get large changes in PCO2 on a daily basis, from, as I said yesterday, from 300 to 800. But most of the reef systems are exposed to ocean water. And I think in most cases, they are, on average, in equilibrium with atmospheric CO2.
Yeah, we see the same in Puerto Rico. It's high.
I think I would disagree. But
Okay, that's not my...
You're mentioning three systems with long residence times.
Yes, and
sort of lagoonal environments,
not barrier reefs and atolls and things like that.
Of course, it depends.
Yes.
Whether you're upstream or
But
downstream.
certainly, like coastal waters for shellfish are frequently high CO2. So I think the idea of thinking about deltas makes sense.
That's a good... Yeah, well, why not? I'm just not convinced by the fact that all coral reefs are... I think it's specific cases when the residence time is high. And I believe that is not a general case for coral reefs, if I remember my previous work.
The second question?
The second question, the dissolution. You should ask Chris. He's in charge of this chapter, and
I haven't read it.
So perhaps you can talk to him at coffee break. Yes, Andrew.
In your CCOB, you said it was set up to do these predictions to help people design experiments where they were mixing things. Does it take account of the dilution effects of mixing two solutions?
What do you mean, the mixing effect?
When you take seawater and a small amount of sodium bicarbonate solution and a small amount of sodium hydroxide, and you mix them to get a final result. Does CCARP handle all the dilutions as well
Yes?
in that?
Yes?
So
I'll show you.
that was why I was curious about how it could handle minus 14 milliliters.
No, by convention, that's an artificial thing. You know, obviously, by convention, the acid additions are negative. The base additions are positive
Right.
in my...
To my mind, that would be the concentration that was negative, not the amount you added.
Well, obviously, I mean, but
You
that's...
multiply one times the other.
Exactly, yeah.
Carries the sum
Well.
through.
But not, you had
Not
one of them
per
as the dilution part.
Oh,
at the bottom.
yeah, gotcha. Yeah.
Yes.
Speaking of your comment about deltas and thinking about one of the questions last night from Chris's talk, one of the things Chris showed was that there's natural variability through time, and how do you account for that? Do you want to model something that's just a dead on, or do you want to capture that natural variability? One way to think about this is to have, for example, the pH stat, a reference probe in the environment that's tracking natural variability, and then have all of your treatments be set offset, so everybody rises and falls together, but you're tracking something that's a natural temporal variable.
Yeah. Often, you know, also people working in estuaries would...
Another way to do that would be to have reported data, so you have a record, and you play the tape of what the natural variability is in the feed.
I've done that with temperature. I take the temperature from a nearby reef, and then I have tanks that are 2 or 3 degrees above that.
I think you could do that with pH potentially.
Yes, Johnny?
A little off the mark here, but I think people probably agree with most of the stuff. But another condition in these things, with particularly with biology, is water flow. So, do you have any comments about how much the water flow rates changing the residence times at very small scales could affect experiments? But I'm sure they do. But I mean, and then maybe this is a part of the discussion that I just want to make sure got brought up early.
Yeah, water flow obviously is, I mean, for corals, we know that very well. I mean, due to the boundary layer effect, there is a strong impact of water flow on photosynthesis and calcification, because the supply of nutrients and carbonate ions and calcium are limited under low flow conditions. Yeah.
Just as a comment on that, in areas where organisms experience oscillatory flow, I've always heard, and some of you biologists can jump in, that oscillatory flow in general is better than turbulent flow, which is in general better than linear flow. So if you can consider those kinds of things when you're designing your experiments, really, I don't think we have good literature or enough information on how those flow effects are actually affecting metabolic rates that I know of. If you guys know of other information on that, that's great, but I really don't think there's enough of that.
And now that you're right, I mean, I don't know of any paper, you know, describing what the flow, I mean, the type of flow is affecting, for example, corals or other benthic organisms. Now that I think about it, I am not sure that this function of adding acid takes into account the dilution effect of the acid. So I need to check that. I don't recall, but I'm not sure.
I had one other comment or question. For people with systems where they're continually flowing water through the system, one difficulty you may have is that the input water composition changes with time. We're starting to track the alkalinity levels at Scripps, and one of the problems we got there is the seawater intake is tied to the pier at a particular depth, but it's a different water mass that's being sampled depending upon the state of the tide. So the alkalinity is varying, integrated through the large header tank that this is settled out and all the rest of it with time. And we're just starting to think how you would cope with that to get a precise understanding of what your organisms were being exposed to. How do you recommend thinking about that?
My solution is just to monitor it, because in Biscayne Bay, we also have, dry spells, so the salinity goes up, the alkalinity goes up, and then we have a rainy season and it drops down. So I'm not thinking about how to control it.
That's, yeah.
Just to know what it is.
We know it's a just slightly different water because the salinity to alkalinity ratio is changing. It's not just freshwater removal or
Yes, the quality of the input seawater is very important, and whenever possible, it would be good to pump deep, and that's below the thermocline when there is one in the summer. That's what we did in Monaco, and the pumping systems pumps water from 50 meters deep, and the quality of the water is really constant throughout.
It's already got PCO2 of 1,500 by then.
No.
They have to degas.
No, not in this area, perhaps in yours, but no, the PCO2 is relatively homogeneous in the water column, and we are stripping anyway. We are controlling the PCO2 afterwards, so that's not a big issue for us. But
I wonder if you might comment on closed experiments where you have an initial chemistry that you start with, and your biology changes the chemistry to your final endpoint, and thinking about plotting biological effects versus your chemistry. Which do you consider, the final or the initial endpoint, or a mean of the two over the experiment?
Usually we use a mean between the initial and final. Obviously, we don't have any measurements in between because.
I think it's important to kind of reiterate what Chris said yesterday. It is a final and an initial measurement.
Yes.
Both need to be done.
In fact, I had a slide on that, and I didn't. Where is it? Forget where it is, but.
I am finding that as a
Yes.
comment on the flow over corals and papers that address that. There's a nice set of papers by Natalie Reichenbach, who's now at UVA, that looks at turbulent, both unidirectional and oscillatory flow over corals and turbulence characteristics, and both within the coral canopies as well as above, and Brian Lowe as well. And they both have a lot of work on coral.
I don't find it. I don't find it, but I have a PhD student co-supervised by Jack Middleberg, and she learned it the hard way. She worked with coccolithophores. I think you know her, Deborah. Her name is Sara Fiorini. And she learned it the hard way because she was doing batch cultures, and she had first to define how many generations were needed, in order to reach a threshold after which you don't want to have more changes in the carbonate chemistry. And for her experiments, she was doing 6 to 9 generations of Emilia huxleyi or other coccolithophores. And when she exceeded that, when the cell density went above 40,000 cells per milliliter, then the chemistry was way off. But if she maintained the cell abundance, within this range, then the changes in the chemistry were acceptable, but still changes in PCO2, I think, were up to 15%. But the two PCO2 conditions, didn't overlap. That's the critical thing, of course. And so it's very important to do preliminary experiments and make sure that the biology during your experiment doesn't change the chemistry too much, obviously. But that's sometimes very difficult to establish. And she had to do the experiments many times before she finds out, And,
I think my recommendation would be for including biology in your experiments to try to monitor more than your initial and final points, because you really lose a substantial amount of information if you don't do that. And there are certainly things that you can't catch. For example, looking at simple things like calcification. You're getting a net measurement over that period of time, and there's certainly diurnal cycles in that parameter, and you miss those if you don't monitor in between, for 24-hour experiments or even short-term experiments. So that you may want to, if it's not already in there, throw that in as a recommendation. Okay, you can do initial and final, but you really probably need to do more than that.
Yes, I fully agree with you, but it is sometimes not possible. If you work with batch cultures of phytoplankton, you cannot have a midpoint. That's just impossible. You just have to live with initial and final. But whenever possible, I fully agree. That's very important to monitor, if you can.
I was thinking about the calcium manipulations and how much do you think we know about the upper limits and the lower limits? Because calcium can be toxic to the cells, and also calcium is involved in many metabolic pathways other than calcification. How well do you think we know about the upper and the lower limits of calcium tolerance?
Okay, I am aware of 3 experiments, involving calcium manipulations. 2 with coccolithophores, and I'm not fully familiar with those. That's Trimborn, Bjorn Rost, and the other one was published a few weeks ago in Journal of Phycology by Nikos Leonardos. The third one is one of mine, so I'm more familiar with that. So what we did, we drove the calcium concentration down to 2 millimoles. And what we did, we looked at, we worked with corals, but we did the same treatment with sea anemones, and we looked at, the photosynthesis and respiration of sea anemones. And we found that, the photosynthesis and respiration were not affected at low calcium concentration in sea anemone. So we believe that, this level of calcium is okay. I mean, it still is enough to maintain the physiological processes that you are mentioning. But the main advantage in the corals is that at 2 millimoles calcium, calcification was 50% or 60% lower. So the CO2 generated by calcification was low, and then we monitored the photosynthesis. And we found that even though the CO2 generated by calcification was lower, still photosynthesis continued unabated. So meaning that, really the CO2 provided by calcification was not useful for photosynthesis. But I have not used levels higher than the natural CO2 calcium level, so I don't know. And I think the guys working on coccolithophores didn't do it either. They stayed below.
I have a largely logistical question about flow-through systems. How do you deal with the changes in water chemistry caused by things growing in the system that you didn't necessarily want to be there? So how do you deal with those changes to phasics in terms of respiration, photosynthesis, and fouling?
Well, if you are in an a flow-through system and open to the atmosphere, I mean, the best would be to make sure that your biomass to volume ratio is low, and that you minimize the changes in the chemistry generated by photosynthesis and respiration. And well, when we do experiments, I think the students, they clean the aquaria several times a week in order to eliminate as much as possible, the algae growing on the walls, and in order to minimize the biological impact on the chemistry. So that's the way we do it.